So here's how I remembered, and this is really, it's simple. And actually, Tristan, this morning you said you made an acronym for something, and I actually did that, I think 2 years ago for this. Because some students I had were like, I don't remember to do everything. I don't remember what to do for a rational function. So I just came up with a head. It makes no sense at all, with your numbers in the head. So A for asymptotes, H for holes, I for intercepts, and P is the last part. That's just points on the curve. Okay, points on the curve. But this is really everything we've done. We've done asymptotes. I put asymptotes and end behavior, meaning the horizontal and vertical and slant. Holes for repeated factors. Intercepts for x and y intercepts. And then, why do you think I have the fourth part there? Points on curve. And I put if needed or if necessary.
Sometimes you just do for plenty of points to get a better idea of what the figure out.
Exactly right, Tristan. Well done. Okay, the asymptotes may not be enough to give me an idea. The intercepts may not be enough, especially with rational functions. So it's going to be useful to plot some points. And we'll talk about what points to plot and how you can strategically choose the right points to plot. That makes sense. So let's look at this first example for today. So we start with the function 2x over x squared minus 1. Now, if we start with this first, we have to think about all of these problems with factoring. Remember I talked about this the other day? I said how the topic on quadratics is probably the most important in here because it's then used later with the whole chapter 8 used it, and now we're again using factoring, which came from quadratics in this section. Okay, we're still factoring. So we start by factoring, and we see this is what we get right here when we factor it. Okay, recognize right away that the denominator is difference of squares, and go ahead and factor it. Any repeated factors in the numerator and denominator? Nothing repeated, so there's no what? No holes in this graph, okay? Because nothing is repeated. So that's the first thing we're going to recognize. There are no holes. There are no holes. After that, we go ahead and say to ourselves, well, we can go in any direction here. So you know what? I'll put a little check up here, by the way. We checked off holes. We're done with that. We got that part done already, part 2. So we should either go to our asymptotes, vertical, horizontal, slant, or go to our intercepts. It doesn't matter what order you want to do. I don't really care. Okay, you don't have to use the acronym at all. It doesn't make any difference to me. Okay, now, what I'm going to notice, though, is that if I want to find my vertical asymptotes come from setting the denominator equal to 0. Because remember, what causes a vertical asymptote is the thing that makes the denominator 0. Whatever makes it 0. But what makes it 0 here would be a 1, and here would be a negative 1. So I have vertical asymptotes. Where are they? One is x equals 1, and one is x equals negative 1. Okay, 2 vertical asymptotes. One is at x equals 1, and one is at x equals negative 1. Because they make the function undefined. If, for some reason, I plug in a 1, and I get 0 over 0, which I don't here, I need to recognize that I forgot about a hole and go back and find the hole. Okay, again, if I plugged in a 1 and got 0 over 0, then it's a hole. But if I plug a 1 back into this function right now, I'm going to get 1 over 0. Or, 2 over 0. Or negative 2. If I plug in the negative 1 here, right, I get a negative 2 over 0. So in essence here, no matter what, if I plug in something for my vertical asymptote, it's got to be something over 0. So there's my vertical asymptotes. Then I look for the horizontal. And for the horizontal, I compare the degrees. So go back to the original if you want. Go back to the original. The original has a lower degree in the numerator than the denominator. So by default, what's the horizontal asymptote going to be if the numerator is less? Y equals 0. Okay, y equals 0, and that's right here. Okay, and it's because the degree of the numerator is less than the degree of the denominator. That's the reason for it there. So I'm trying to circle and highlight things now, because I didn't do this that much when we were going over the lesson. This is stuff that you need to do. Literally, everything I've highlighted and pointed out are the key points. If I'm looking at my notes and I'm studying, and I don't want to read through everything, or I don't want to go through stuff, or if I'm learning about this, because in college, honestly, you guys, you're going to have assignments where you have to read the chapter, or read the math section, and then you go into class in college, and then you learn about it in class. But reading ahead of time is huge. It's so important. So here, I'm trying to explain how, if I'm reading these notes on my own, and I'm trying to learn about this, and I were highlighting in the textbook, because you buy your textbooks, right? You highlight your own book, this is college, what I mean. You'd be highlighting all the important stuff here, and that's what I'm showing here. Now, we've got our intercepts. Check. What kind of intercepts do we have? Vertical, and in this case, horizontal. What happened to the slant intercepts? Good. Whenever there's a horizontal, there's never a slant. Whenever there's a slant, there's never a horizontal. Is that clear? Okay, it's never going to be the case we have both of those. You can have vertical with one or the other, obviously. We have that right now. Now, once we have the asymptotes, once we have the actual holes in the graph, we then go on to our intercepts. Okay, so let's go to part 3 now. We'll check that off. We're going to do that. So to find the intercepts, just as Bridge said, set x to 0 to find the y-intercept. Set x to 0 here. You get 0 over negative 1. What does that mean? What's 0 over anything, though? 0 over anything is just 0. So if I plug in a 0 for the x value, I get 0 over negative 1, and 0 over negative 1 is just 0. So this is what the y-intercept is. 0, 0. Any reason it's not a coincidence, but why do you think it's 0, 0? George? Because what? Yeah, it goes to the origin. How else do you know that, George? There's another reason we know it goes to the origin besides the y-intercept. The x-intercept. If the origin is one of my intercepts, it's both of my intercepts technically, right? Remember, an intercept is when a function value x or y is equal to 0. Well, if they're both 0, that's both intercepts. How do I get x-intercepts? How do I get x-intercepts? Always, guys, always.
Set y to 0.
Set y to 0. So please take a look up. This is what we're talking about right here. This is the stage we're at. So we set y to 0. Now, remember, you can think of this 2 ways. I've been trying to teach you guys the mathematically correct way to think about it. How can a fraction equal 0 if the numerator equals 0? The other way to think about it is if you want to. It's not really correct. It's kind of a weird way. Multiply both sides by x plus 1, x minus 1. What does it make this side still? And what happens over here? If you multiply by x plus 1, x minus 1. Yeah, they cancel, meaning we just simply 2x. So if you want to think about, all right, you know what? Multiply everything by whatever's in the denominator to clear it out. If you want to do this, you can, but it's a waste of your time. Okay, but if it helps you for now to understand, go ahead and do it. But these would cancel with these. You'd be left with 2x over here, and then 0 times anything is still 0. So you would end up with 0 equals 2x. But you'd still get 0 equals 2x. Because 0 times anything is 0, and then these would cancel. In the end, solving for x divided by 2, 0 divided by 2 is still 0. And lo and behold, like we predicted, the x-intercept is also 0, 0, the same as the y-intercept. Questions so far? We've done everything we've done in E1, E2, and E3 already. Maybe I'll give you another quiz tomorrow as a chance of redemption. Would you like that?
Yes.
If you got 100 or something, I'll let you go free though, okay? If you did well on this one, I'll let you go free on it. But I'll give you another quiz tomorrow on E1, E2, and E3. Okay? Intercepts, holes, and asymptotes. Wow, forgot that word for a second. Okay, tomorrow. We're going to continue with this still though, so we're not going to get to the graphing part just yet. So if you want it tonight, practice E1, E2, and E3. I'll let you replace your old quiz with this. Show me that you can actually do a little better than... So we did a lot of this yesterday, and we highlighted, underlined all the important stuff. So we need to take all this stuff and put it on a graph. Now, if I take all the stuff from asymptotes, holes, and intercepts, and put it on a graph, go to the next page, please. I will get the graph at the top. So please only look at this for now. This is what I would get if I were to graph everything from the last example. We had a vertical asymptote at plus or minus 1. We had a horizontal asymptote at y equals 0. We had an x-intercept of 0, 0, and a y-intercept of 0, 0, turns So this is what we have, literally. Is that enough to graph? Definitely not. You can't graph with just that information. That's definitely not enough information. So here's what I need to think about now. The points that are more important are the points near the asymptotes. And when I say near the asymptotes, I'm referring to the vertical asymptotes because I'm referring to x coordinates. So we're going to make a table, and we have to pick strategic x values. X values that will help us to determine the y values, and as a result, we can determine the shape of the graph. Is the graph going to be here? Is it going to be here? Is it going through? Is it up here? Is it down here? Is it where is this graph going to be? So what we do is we identify our asymptotes, the vertical ones only, and pick x coordinates nearby. So over here, this is -1. So we'll probably pick points like -1.5, -2, -3, something very close, and then a little bit further out. In between here, we probably pick like -0.5, 0 we already have, pick +0.5 to get on the point, maybe 0.75 or something. Out here though, I pick probably like 1.5, and then 2, and then maybe 3 and 4. So I do this because the behavior about the vertical asymptote is the part that's the most intriguing. We need to see what happens around the vertical asymptote. So I make a table over here of all those values I just mentioned. So I went to -1.5, to -2, to -3, and I did 1.5 and 2 and 3. And then I also did what I showed you here, 0.5, -0.5, 0.75, -0.75. Look at all these y values. What good are they to me? What good are these y values to me? George?
They help you plot it.
They help me plot the shape of the graph. They help me get an idea of what the graph should look like. So I need to take these values and put them on the graph. So if you want to, go to the blank graph first to practice this. Don't look at the answer yet. Go to the blank graph on your work. Zoom in on this graph right here, please. Okay, and I'm going to put the table up right here. Take these points and plot them on the graph. Use the empty graph, please. Do not use the completed graph because it's already done for you. Use the empty graph and plot these data points on there. And try to visualize what would be happening or what the shape of this function would be based on these points. And think about it as a smooth connect the dot graph that cannot cross the vertical asymptotes. So when you're connecting these dots, remember that you're not going to cross over a vertical asymptote. If you need to, you can cross the horizontal, but never the vertical. Notice a lot of these come out as fractions when you evaluate them. I would personally just put this right in the calculator and come up with a table. Although actually on the test I probably won't let you use a calculator, so maybe just being able to simplify your fractions, okay? Because look at all these messy decimals here, right? See how messy they are? So it's just going to be annoying to get these data values, but I'm going to have to practice. The fractions are going to get a little bit messy practice upon that. Now, if I plot these points on this empty graph, I'll end up with what I see here on this graph. So if you plot these 3 points on the left, these 3 points on the right, we'll see that they stay in their regions. Remember, what do the asymptotes do? They create boundaries. So here's what I want you to think about. This is like its own region right here. Follow the cursor, please. This is like its own region. This graph is bounded by the vertical asymptote here and the horizontal asymptote here. This will get closer and closer and closer, but never touch this. This function will get closer and closer and closer to the x-axis, but never touch the x-axis. The same thing occurs in this region over here. Okay, this is its own region from here to here. Okay, this little region is segmented off. This is an empty region. This is an empty region. They're not used. It's fine. These regions are not used. A lot of rational functions exhibit some sort of symmetrical behavior. And in the middle, what we notice is we have almost what looks like a cubic function. Okay, it looks similar to a cubic function from earlier this year. So we've got 5 data points in the middle, and in the middle we can see that this function does cross the horizontal asymptote. The horizontal asymptote is in red. It is crossed right here at the origin. So again, please note this. Horizontal asymptotes can be crossed. It's as they tend to go to the ends that the function gets toward the asymptote. But in the middle, you can easily cross it. Here, an example of a horizontal asymptote that is crossed many times. A perfect example, and I've used it already in this class. You hit a speed bump in a car. You know those little speed bumps in the road? The car oscillates, and here's what it looks like. Okay, I think I went over this at least once already. This has a horizontal asymptote, and its equation is the x-axis. But this function is an oscillatory function that crosses that over and over. So although, I'm putting it in red, if you can see it in red right now. Although there's a horizontal asymptote there in red, the actual function crosses back and forth over that asymptote, but eventually it tends to go toward the asymptote. And again, the horizontal asymptote has to do with, what was the phrase? What kind of behavior? We're looking at the behavior toward the ends. We called it the end behavior. This is really a function that eventually teeters off, or like stops oscillating over and over, and you get this. So eventually, the end of this function is the line y equals 0, and it goes on. And I'm doing this on purpose because what happens, right? Once you stop oscillating in the car, your behavior is that you're now level with the ground forever. So that the end behavior is what your car eventually does. It hits the oscillation, but eventually your car settles out. Okay, until you get to speed up, obviously.
So a function like that, there is a point. It's not really oscillating.
It eventually would stop because of what's called damage here. But theoretically, if you had a spring and there were no friction, and you pull spring and let go, it would oscillate forever. Because this friction exhibited, it loses thermal energy or heat in the coils. So as a result, it eventually loses thermal energy, which loses motion, so it does eventually stop. So this would be one where it does eventually get to the asymptote. Remember, guys, that it's the idea that you're going toward a value. In this case, it's reaching a value. The value of the function is 0 that it's reaching. And then it reaches that when it stops oscillating. But our rational functions here, their idea is that they get closer and closer to the horizontal. So this one, it could cross over and come back over like that, but it's not going to. Okay, a lot of these are not going to do that. Yes?
Is the point of origin like the point of inflection?
Very subtle, but yes. Absolutely, George. Very good. Notice here, follow the cursor, please. Follow the cursor. If I continue this curvature, it would curve back, right? This is like a little half of a parabola, or this is the half of a parabola right here. This is concave down right here. And this, if I curled this around, it technically curls back up like that almost, and that'd be concave up. So there's positive concavity and then negative concavity. So this would be considered, yes, a point of inflection. Okay, it's not a double root or anything, or a triple root rather, where we had that earlier in the year. A triple root caused a point of inflection. This is a point of inflection for a different reason. Okay? It's a great question, George. Good point. Let's move on to the second example. So in the second example, we recognize right off the bat that the numerator factors, but does the denominator factor for this? Just look at it. Can you factor that? No, you can't. 2x squared plus 1 does not factor. It doesn't factor here. The numerator does. So here's what we've got right here. So we start with factored form always. This is very useful, right? Every time. Factor it so you know what you've got. Next, why are there no holes? Who can tell me the reason for this? Why are there no holes here? Bridge?
If you can't factor the bottom, then you're not going to end up with anything the same all the time.
Exactly. There can't be a repeated factor in the top and bottom if the bottom can't be factored to start. Right? So you're not going to repeat a factor anywhere, so there are no holes. Now, we look at the denominator and say to ourselves, normally we would factor it and set it equal to 0 to get the vertical asymptotes. Okay, normally again, we would set the denominator equal to 0 after factoring it. So I would factor this function and say, okay, set each of these factors equal to 0 and give me the asymptotes, right? But there's no factors now. So I need to set the whole denominator equal to 0. And by doing so, I get this right here. The whole denominator equals 0. Move 1 over. It becomes negative. So it becomes plus or minus the square root of negative 1/2. And as a result, there are no vertical asymptotes. This was one of those instances we said. Because the answers that would make the denominator 0 are imaginary. Pick any number. When you square it, what does it always become? Any number squared is always, any real number squared is always positive. So look at your denominator, folks. How is it possible to get that to be 0? I want you to see this from a different perspective, so please look at this. If this must be positive, and you're adding 1 to it, could this ever be 0?
No.
The denominator can never be 0. Again, I want to so you can see it both ways. First, it cannot be factored. Set the denominator equal to 0, you get imaginary answers, which means there's no vertical asymptotes. To prove that, though, think about what causes vertical asymptotes. It's caused from the denominator equaling 0, but look at it, literally. Anything squared is positive, plus something makes it more positive. So there's no way by inspection alone, by looking alone, that this can give you 0. So there's no way you can have a vertical asymptote for this problem. Is that clear what I'm saying? Okay, there are no vertical asymptotes. It's one of those rare times where you won't have vertical asymptotes because the denominator will never be 0.
If you graphed it on an imaginary plane, would it be different?
But it's different though. Imaginary planes are not drawn the same way. So we're going to say for now that you just can't even graph this actually. The imaginary plane is graphed with like numbers like 2 plus 7i. That's all it's graphed with. Not with things where the roots are imaginary and asymptotes are imaginary. Okay? That's a great question too, guys. We're not worried about the imaginary plane right now, but I did mention that this year, so good to note. How do we know it's a horizontal asymptote of 1/2? Why is this true? Why is it a horizontal asymptote of 1/2? Where's the 1/2 coming from, George?
The ratio of leading coefficient.
Good. When the degrees are the same, as stated here, dn equals dd, we look at the ratio of the leading coefficients. This has a coefficient of 1. This has a coefficient of 2. There's the 1/2 at the top. Here's a 1 up top. The equation is 1/2. And since it's a horizontal asymptote, it's y equals. So many of you are not putting x equals and y equals. You got to do that. Okay, there was one thing I looked at just now. I saw a couple here. Y equals 1/2 because it's horizontal. When it's vertical, x equals whatever the number is. Okay, make sure you understand that horizontal lines are y equals some number. Vertical lines are always x equals some number. And you can see that because look at the denominator. To get the vertical asymptote, wouldn't you solve this anyway? It would be x equals. That's what you'd end up getting. Solving this, we got x equals plus or minus root negative 1/2. Well, had this been a real number, these would be your asymptotes, and they would be x equals. It comes right out of the actual equation or expression in the denominator. George?
So if instead of saying like horizontal asymptote at 1/2, you have to say horizontal asymptote at 1 equals 1/2.
It should be y equals 1/2 because you're giving the equation of the asymptote. Okay, but if you said horizontal asymptote at 1/2, I know what you mean because it says horizontal. But if it says list the equation of the horizontal asymptote, which you probably will in the test, typing you through, you should write it as an equation. Okay, you could say HA and then below it y equals 1/2, or 1/2 in this case. The y-intercept, just set x to 0. To do that, cover these up right here. You get -9 over 1, or simply 0, -9. Notice I write my intercepts as coordinates. This should not be written as y equals -9, because that looks like it's a horizontal asymptote, right? Look up, guys. Here's the horizontal asymptote, y equals 1/2. If I write y equals 9 here, or -9, it's really interpreted as another horizontal asymptote. There's only one. Okay? There's only one. And then I'll highlight it. Old show. So -9 is the coordinate of the y-intercept. Okay, not y equals -9. The x-intercepts, where do they come from? They come from setting the numerator equal to 0. So we technically set the whole function equal to 0 right here. We then recognize when can a fraction equal 0? Only when the numerator equals 0. So set the numerator equal to 0 and get your x-intercepts. So we've got our y-intercept and our x-intercepts. If we only graph what we know, here's what we've got. Okay, let's make this clear before we go further. If we only graph what we know, this is what we've got. It's never enough, really, these problems. Recognize, please, that the asymptotes, the intercepts, the holes, they're guiding values. They're guiding values. They're not enough ever. And clearly here we can see that. We don't even have a vertical asymptote. We don't have a hole, nothing. So it looks like we've got two coordinates here. That's definitely not enough. 3 coordinates, sorry. Right? 1, 2, 3 coordinates. That's definitely not enough. So since I don't have vertical asymptotes, it's hard for me to choose what points I want to pick. Well, it makes sense to choose these points, right? Because they're in between as x. And if I can plot the coordinates, maybe I can at least know what the curvature looks like. It's got to be something like a parabola or a V or an inverted V, something like that. So I need some coordinates so I can interpolate, right? I can sketch the graph between 2 points, interpolate, not extrapolate, but interpolate what this graph looks like in between these coordinates. So for the x values, I'm going to choose -2, -1, and -0.5. That's here, here, and here. The question is, where are they on the y values? Here they are, right here. So if I'm going to plot these, I'm at -2, -0.5. That's about right here. Then I'm at -1, -2.67. That's about here. And then I'm at -0.5, -5.83. That's about here. Okay, and what do you think is going to be on the other side for this kind of a graph? What do you hypothesize? Based on the x-intercepts and the way this graph looks already, what do you think will happen on the right-hand side? Hannah? Yeah, it's symmetric. This one happens to be symmetric. Okay, so if I want to see what the graph looks like, I plot those points, and then I connect them. Okay, and then I connect them. Do you know if it's going to be like a V at the bottom or a smooth curve? No, you don't really know. Okay, you really can't tell that just yet. You know what I'm talking about here at the bottom? Is it like a smooth curl? Is it a V shape, literally coming to what's called a corner? In calculus, we call that a cusp or a corner. When it comes to a location where the rate of change is linear on one side, and on the other side it's like this, or it's also linear on the other side. When it's a smooth curve, it's not called a corner, it's a min or a max. So in this case, you have a minimum value here of 0, -9. That would be a minimum coordinate. A minimum coordinate. Okay? I saw a hand pop up at some point. I was kind of overlooking it. Yeah,
So not all of them are symmetrical, but
no, they're not all. It's a great question, Nat. Let me think for a sec. Well, mathematically it can be proven. Let's go with that first. That's the easy way to do it. If I look at the numerator and denominator, I can see it right away mathematically. Because look, what coordinates did I choose for my table? Look at my table. Didn't I choose opposites for the x values? Look at the x values. Everybody here, please. Aren't these all opposites of each other? These are opposites, these are opposites, these are opposites. And these values became the same. Look at the actual equation. Are you squaring the x value in 2 spots and nothing else, right? When you square a positive or square a negative of the same number, isn't it the same result? So as a result, these have to be the same, these have to be the same, these have to be the same. You call this an even function. A function which is even involves only exponents that are even. Is that clear? So if everything is x to the second or x to the fourth or x to the sixth, then you know the function will exhibit vertical symmetry. Vertical symmetry. You can have what's called rotational symmetry through the origin with an odd function. You'll learn a lot more about that in pre-calculus. Okay? It's a whole topic in pre-calc, odd and even functions. Odd and even functions. Very useful, very necessary too. It helps you to graph stuff a lot easier. All right, let's press on the next one. Actually, where are we at in time? Yeah, okay, so we're a little bit before 11. Try this one. We got about 4 or 5 minutes left in the period. Try this one on your own real quick. Make sure we get through it, and then maybe somebody can just go through it. Explain the whole problem. It's all written for you already, but explain physically what's happening and why it's happening once you spend a couple minutes looking at it. If you've already done this one, I see a couple of you are moving on and you're on the next one, that's fine. But when we go over this one, maybe you can come back to it to explain to others. So again, I'll give you like a minute or two to read through this. Just read through it. It should be pretty straightforward when you're reading through the problem. Literally, read the text like it's a paragraph. You could practice always. I think it's good to practice. So the table itself has the values. Then you can practice graphing them, or you can even practice calculating all those values by hand, because it could get messy. See that? Guys, can I pause you for a second and give you a huge hint? Huge hint. This will help you enormously, especially for those that struggle with time on tests. Listen carefully. When you're plugging in the x values in the table, it's going to get really messy, right? Because it's going to be a lot of fractions. You're not going to want to square and cube things. So take the x coordinates from the table here. See those x values? Plug them into the factored form. It makes life easier. Okay, that's a little hint I didn't talk about yet. Because if you plug it back into the original, you're going to have to do like 0.5 squared, and then you're going to get wild decimals, see what I'm saying? Use the x values in the table that you pick, which are fine, but plug them into the factored form of the actual function. And if something was a whole, if there were a whole and you could cancel, you can plug it into the reduced form to make it even easier. See what I'm saying? Everybody clear on that? So if you cancel factors, if there's a whole, and you have a reduced, simplified form now, because those factors that canceled are gone, plug the x values into the reduced or simplified function, it makes life even easier. It's less to do. Okay, so jot those notes down at least, please, so you know to do that. So, George, if you want to practice doing that with the coordinates and coming up with the y values here, take them and go ahead and just plug them in up here. Okay? And you should be practicing graphing these values as well. 1103 or 1101? 01. All right, so who wants to explain this? Who wants to? It doesn't have to be the whole thing, but at least the beginning to start us off with. What's physically happening? What do we do to begin a problem like this? Go through the process. Go ahead, Bridge.
Okay, so first you factor the top of the numerator.
Very good.
And then you realize there's no holes because there's no x minus 2 in the numerator. So, and then in the denominator, the vertical asymptote is positive 2 because that would make the denominator equal to 0.
Very good, Bridge, because it makes a 0 there, 2 minus 2, and it's x equals. Continue.
Okay, and then next you look at the numerator, and the degree is greater than the degree of the denominator, which means you have a slant. So then you plug in your vertical asymptote of positive 2 in synthetic division.
Remember, we plug in whatever the opposite of this number is, which happens to be that. Good. You get this as a result. Go ahead.
You get that as a result, and then the slant asymptote is x plus 6.
Very good.
And then for the y-intercept, you plug in 0 for x. And for the x-intercept, you set the numerator equal to 0.
Set the numerator, these two. You get negative 5 and positive 1. Negative 5 and positive 1. Yes? Remember, it's whatever's in the beginning of your synthetic division result. You drop. Remember, the whole idea is that it's end behavior. Plug in infinity, this thing goes to 0. You end up with this as a result. Okay? Just so you can see what it looks like as a result, okay? So listen, where are we at now? That was example 3 or 4?
I think that was 3.
3. All right, so listen, tonight, you have 2 nights. Tonight, I originally put homework due tomorrow. Okay? For this section, the homework was due tomorrow because on Friday the project is due, right? Think about it. Friday the project is due. Tomorrow you don't have class. So listen carefully, please listen. Tonight, watch the rest of the examples. 4, 5, 6, maybe even 7. The last one I will go over though, for sure. So watch the others. Have that homework turned in by Friday. But your project is due Friday also. I'm giving you another day on the homework, but don't come to me later and say, I had both things due. Okay? Original homework is due tomorrow, but we're a little behind. So I'll push the homework due to Friday, but both of them are due Friday. We got it. Yep. Thanks. If you want your quizzes, come by after school for office hours. They're going to be there at least. If not, just come by to get extra help too.